In this video, we are going to have a look at 5 different sorting techniques and visualize how the sorting is carried out in each. The 5 sorting techniques we are going to see are bubble sort, selection sort, insertion sort, merge sort, and quick sort. We are going to visualize and see how these sorting algorithms perform over 4 different data sets, such as a random data set, a completely sorted data set, a reverse sorted data set, and a partially sorted data set. Let us quickly have a look at each of these sorting techniques. Bubble sort is a brute force sorting algorithm where every element of a data set is compared with every other element in it and swapped whenever it is not in order. Since every element is compared to every other element, the number of comparisons made is equal to n square, where n is the size of the dataset. Selection sort follows the same principle as bubble sort, except the swapping of elements is done only once per element. The maximum number of swaps which are done in selection sort is n because every element can be swapped only once. Insertion sort is done under the assumption that the subset of elements before the element being checked is always sorted. The element being checked is then inserted into this sorted subset in order. The element being checked is checked against the largest element to the smallest element of the sorted subset present to decide where it is to be inserted. Merge sort is a divide and conquer algorithm where first the dataset is broken down into n elements and these n elements are recursively merged back together in sorted order. Breaking down a dataset into n subsets is done by recursively breaking down every set into 2 subsets. Quick sort is also a divide and conquer algorithm where the sorting is carried out while breaking down the dataset into subsets. Unlike merge sort, the sorting of elements is done during the divide step itself. Since these 5 algorithms run differently, their time and space complexities vary. Quicksort and merge sort are the best in terms of time complexity. This means that they take less time to compute than the others. Bubble sort, insertion sort, and selection sort are the best in terms of space complexity. This means that they consume less memory during computation than the others. Now, let us see how these sorting techniques perform over the different data sets by visualizing it using a tool I have developed. First, we consider a dataset with random values in a random order. We are setting the dataset size to be 100 and its sortedness to be 0% for it to be a random dataset. The red bars indicate the elements of the dataset that are being compared. We can see that the divide and conquer algorithms are recursively dividing the dataset. As described in insertion sort, every element is inserted into the sorted subset present before it. Bubble sort and selection sort take the same amount of time since they are very similar and only differ in the swapping mechanism. For a random dataset, quick sort and merge sort complete first, followed by insertion sort, selection sort, and bubble sort. A reverse sorted dataset is one in which the dataset is sorted but not in the order we need. In this case, it is sorted in descending order when we need to sort it in ascending order. The settings for generating this dataset is the same as a random dataset, except we choose the reverse sort option. Quicksort sorts the dataset in a single iteration but does not complete as it has to ensure that the subsets are sorted too. Even though bubble sort and selection sort follow the same principle, we can clearly see how the swapping is done differently in each sort, with selection sort doing only one swap and bubble sort swapping all the elements. Insertion sort takes longer because every element has to be inserted in the first position of the subset after comparing it with all the values of the subset. Therefore, for a reverse sorted dataset, quick sort and merge sort complete first, followed by bubble sort and selection sort, and finally insertion sort. A partially sorted dataset is one in which a percentage subset of it is completely sorted. We are going to test a 50% partially sorted dataset. As you can see, the first half of the dataset is completely sorted. Since the first half is sorted, the time taken by merge sort to sort the first half is comparatively lesser. Therefore, merge sort completes before quick sort. Insertion sort runs a little faster than usual because the sorted subset is present in the beginning and comparisons need to be made only after the sorted subset, that is, the middle of the dataset. The sortedness of the dataset does not make much of a difference for selection sort and bubble sort because the number of comparisons made are going to be the same. For a partially sorted dataset, merge sort completes first, followed by quick sort, insertion sort, bubble sort, and selection sort. What if the dataset is already sorted before we run our sorting algorithms on it? We are going to test a 100% sorted dataset. Insertion sort completes quickly because every element is compared with the element before it and inserted at the end of the sorted subset. For a dataset of size n, only n comparisons and insertions are made. The sortedness of a dataset does not make a difference for selection sort and bubble sort because the number of comparisons made are going to be the same while the number of swaps are going to differ. Therefore, for a completely sorted dataset, insertion sort completes first, followed by quick sort, merge sort, bubble sort, and selection sort. From running these simulation experiments, there are a few relationships between performance parameters that are found. The primary parameters are size of the dataset and sortedness of the dataset, and the secondary parameters are time taken to sort and memory consumption while sorting. For all sorting algorithms, as the size of the dataset increases, the time taken to sort the dataset also increases, some more drastically than the others. As the sortedness of a dataset increases, the time taken to sort the dataset decreases for merge sort, bubble sort, and insertion sort. The sortedness of a dataset does not seem to have an effect on the time taken to sort for selection sort and quick sort. As we saw, for a completely sorted dataset, insertion sort performs the fastest. The memory consumption for merge sort and quick sort are higher because they are recursive in nature. The memory consumption for merge sort fluctuates because of the copying process involved in it. For all sorting techniques, the memory consumption increases with the size of the dataset, some more drastically than the others. The main question is, which sorting technique is the best? That depends on the dataset and the environment in which the sorting is to be done. So let's rephrase that question to, how do we know which sorting technique to use? Choosing a sorting algorithm for a dataset whose size or sortedness is known can be done because the relationship between the size, sortedness, time, and memory have been established. If the size and sortedness of a dataset are unknown and there are constraints on the time taken, quicksort and merge sort will be preferred over the other sorting techniques. If the size and sortedness of a dataset are unknown and there are constraints on the memory consumption, insertion sort, selection sort, and bubble sort will be preferred over the other sorting techniques.